we'll continue our discussion on this topic of refraction of light at a plane surface. So far we have looked up to the aspect of normal shift. We'll now continue our discussion from this point onwards. That is, we will be discussing about total internal reflection. We'll talk about critical angle and the relationship of critical angle and refractive index, and finally we look at some of the applications of total internal reflection. So we're going to start our discussion with total internal reflection. So remember, when we talked about refraction, we mentioned that when there is a source of light here and when there is a source, if this is the angle of incidence, then this would be the angle of refraction. This is the angle of refraction, this is the angle of incidence. So let us assume for the time being that this is a denser medium, this is a rarer medium. Rarer medium. That means this is an optically denser medium, optically rarer medium. Now let us consider a source here, O. So when the light travels from this end to the surface at the other end, at O, the angle of incidence is I and the angle of refraction is going to be R. Now we also know that when light travels from a denser medium to a rarer medium, the light bends away from the normal. So in this case, since the source of light is in the denser medium, this ray is moving away from the normal. That means R is greater than I when light travels from denser medium to rarer medium. So let us extend this much further, this logic much further. So let me say that there is another ray of light that is meeting this layer at this point. Now this angle of refraction is going to be much larger. This is the angle of refraction, R2 is going to be much larger because this angle of incidence is larger now. So larger the angle of incidence, larger is going to be the angle of refraction, and the angle of refraction is greater than the angle of incidence. So let me extend this much further, and then let me take one more ray of light which is meeting this layer at an angle of C. Let me call it as C. Now in this case, the angle of refraction is such that this refracted light will just graze through this. This will be the refracted light, refracted ray. So notice that as the angle of incidence keeps increasing, the angle of refraction also keeps increasing when light travels from denser medium to rarer medium. Because in this case, the refracted ray is moving away from the normal. So at some angle of incidence, C, the refracted light just grazes through the surface of the medium where the denser medium and the rarer medium meet. So this is the angle at which we have refraction at the angle of 90 degrees. So this angle will be 90 degrees. So if there is another ray which is traveling at a much larger angle of incidence than the critical angle, then this ray would get totally reflected. So extend this logic much further. if there is a ray of light that is incident on this surface at an angle greater than this angle C, then this ray of light will get totally reflected. There is no refraction happening at this point of time. This process is known as total internal reflection. That means 100% of the radiation that is falling on this, or 100% of the rays that are falling on the surface will get reflected internally. There is no refraction taking place at this point of time when the angle of incidence is greater than the angle called C. And now let us look at some of the concepts here. This is about total internal reflection. So total internal reflection can occur only when light is traveling from a denser medium to a rarer medium. It cannot happen when light is traveling from rarer to denser. So this occurs only when denser medium to rarer medium, when light travels from denser medium to rarer medium. So let me go back to this concept of total internal reflection. So at some angle of incidence C, the refracted ray grazes the surface here at this point, where the angle of refraction is 90 degrees. That angle of incidence is called as the critical angle. So if the incident ray has an angle of incidence greater than C, then there is no refraction taking place. The rays get reflected back into this medium, into the denser medium again. So this concept is known as total internal reflection. The ray is totally reflected internally. And that is the reason it gets a name total internal reflection. So there is reflection of light within the medium. There is no refraction taking place. This is the concept of total internal reflection. And for total internal reflection to happen, two things need to happen. One is light should be traveling from denser medium to rarer medium. Light should travel from denser medium to rarer medium. And the second aspect is the angle of incidence of light should be greater than the critical angle. The angle of incidence of light should be greater than the critical angle. So what is critical angle? Critical angle is that angle for which the angle of refraction is 90 degrees. So let me write it down here. So critical angle is the angle of incidence when light travels from denser to rarer medium is the angle of incidence for which angle of refraction is 90 degrees. So critical angle is the angle of incidence for which the angle of refraction is 90 degrees. That means this refracted ray grazes the surface here. So I made a mention here because for refraction, for this to occur, for this phenomena to occur, light should be traveling from denser to rarer medium. So this is what we mean by critical angle, and if the light is incident on the surface at an angle greater than the critical angle, then we will find total internal reflection. So total internal reflection is a phenomena in which light incident on this surface gets totally internally reflected or totally reflected inside the medium. So that's about total internal reflection. And then about critical angle. So after having looked at this concept, let us now try to find out the interdependency of critical angle with refractive index. Let us see how we can express critical angle in terms of refractive index. So I hope this aspect is clear. Now let us move on to the next topic, that is critical angle and refractive index. So let me retain this diagram for the time being as I work out this. So we mentioned that for critical angle, the refracted ray makes an angle of 90 degrees with the normal, and therefore if C is a critical angle, then we have, let us assume that N1 and N2 are the refractive index of this denser medium and rarer medium, and light is travelling from denser medium to rarer medium, and we are observing refracted ray at 90 degrees to the normal, and therefore we have from Snell's law, we know that N1 sine C is equal to N2 sine 90 degrees. So sine 90 is 1, therefore this is N2. And if you are considering air as a medium there, for air N2 is equal to 1, and therefore we have, and let us assume that, and let us say instead of having N1, let us say this is the refractive index N, therefore we will have N sine C is equal to 1, or N is equal to 1 divided by sine C, or alternatively I can write sine C as 1 divided by N. So this is the expression I get for C, that is a critical angle. So critical angle for a medium is such that sine of that angle is equal to 1 divided by N, where N is a refractive index of this medium. So I have sine C is equal to 1 divided by N as the expression linking critical angle in terms of refractive index. Likewise, I can also state N is equal to 1 divided by sine C. So note that we just used Snell's law as the starting point, and we said N1 into sine C is equal to N2 into sine R, which is R is 90 degrees here, and therefore I have it as N2. And for air, N2 is equal to 1. This is air, so N2 is equal to 1. I consider N1 as, instead of N1 I have it as N here, because N stands for the refractive index of the denser medium. So N sine C is equal to 1, or N is equal to 1 divided by sine C, or alternatively I have sine C is equal to 1 divided by N. So after having looked at the concept of total internal reflection, about the critical angle, and having defined what the critical angle is, and after having looked at the expression for critical angle, now let us move on to the next aspect, that is applications of total internal reflection, and we will be considering optical fibers as one of the applications for total internal reflection. So let us next look at the applications of total internal reflection. So incidentally, total internal reflection as a phenomenon was observed by a scientist by name Tyndall. Incidentally, he pointed light at water that is coming out of a tank, and he observed that the light followed the curved path of the water, and that's how the concept of total internal reflection occurred to him. Okay. Now let us look at the applications of total internal reflection. So let us look at the application of total internal reflection. Here we are considering optical fibers. So an optical fiber is basically thin strands of glass fiber held together. So, and each glass fiber here is has a diameter equivalent to that of probably the human hair. So that is the size of the dimensions or the diameter of a single glass fiber. So we have several such glass fibers. They have a coating, outside coating of a glass material, of a different glass material that has a lower refractive index. So we take such glass fibers, group several of them together, and as I mentioned, each one of the glass fiber has a diameter equivalent to that of a human hair. So we take several such glass fibers and hold them together. The ends are clamped firmly, and then the sides are polished. These sides are polished. So if you have such an arrangement, then even if you bend this fiber, this optical fiber, light gets transmitted through this. Optical light gets transmitted through this. The reason being, it is because of total internal reflection. It's using the concept of total internal reflection. So when light is incident at this angle, because of the refractive index of this material being less than the refractive index of the outside, the rays undergo total internal reflection. So these light rays gets totally internally reflected, so there is absolutely no loss of information, and light travels along this, even along curved paths. So that is how this light that I shine here gets transmitted at the other end, even though this fiber could be going around curved paths, because it uses the concept of total internal reflection, and all the light that is incident here gets internally reflected. And as I mentioned, these optical fibers are made up of thin strands of glass fibers held together and polished at the ends. So this is about the concept of optical fiber. Note that in order that there is not much loss of information when the light is sent from this end, these fibers have to be nearly parallel to one another. These individual fibers, glass fibers, needs to be parallel to one another and should be held firmly at these ends. Also, we will have a coating on the outside of this glass fiber to prevent scratches on the surface. So these are the two aspects that need to be borne in mind about optical fibers. Now after having looked at optical fibers, now let us look at the other example that uses the concept of total internal reflection. These are what are known as total reflection prisms. Total reflection prisms. So these prisms are basically of glass and or right angle triangled. Glass prisms that are right angled. So we have, this is 90 degrees. So when light falls on that, it gets totally internally reflected and moves along this path. And now we have one more here, which is of this shape. So this is 45 degrees, this is 45, and this is 90. So the light is made to incident on this, it gets totally internally reflected. Incidentally, I made a mistake here. Let me rewrite this. So this is the diagram for the beam inverted. So I have the prism here, and I am considering two lines of two rays incident here. They get internally reflected and emerge from the other side. The angle of incidence has to be either greater than or equal to 45 degrees for glass, because 45 degrees is the critical angle for glass. So this is the first type of prism I can have, which shows total reflection. And then this is the second type I have, where the beam gets inverted. So if there is an image of this size, of this type, then on the other side I find an image that is inverted. Effectively the beam gets inverted because of total internal reflection. These types of prisms are used in optical lanterns. These types of prisms for beam inversion are used in optical lanterns. And now there is a third type of prism that is used here, and that is shown in this diagram, where the ray gets turned through 180 degrees. These type of prisms are used in what are known as binoculars. So binoculars use these types of prisms, optical lanterns use this type of prisms. So these are the three different configurations that we can think of which use the concept of total internal reflection. Listed here are some of the applications of optical fibers and therefore the concept of total internal reflection. The first one is optical fibers are used in communication. So they are replacing thick copper cables for transmitting information. Then in many aircrafts, control signals are fed from the pilot to the control surfaces using optical fibers. The advantage here being that these optical fibers, when they carry information, are not the information is not distorted because of external factors such as electric charges or magnetic field, external magnetic field or external electric field. And that is the reason we use optical fibers in such communication purposes. And again, optical fibers are used in medical fields to visually examine the interior parts of a human being, such as the stomach, heart, etc. And finally, optical fibers are used in refractometers. These refractometers are used to measure the refractive index of liquids. There are several other uses of that use optical fibers, but I am limiting the list to just 4 of them. With this, I am concluding the session on the topic of refraction at a plane surface. I hope these concepts are clear to you. Thank you very much.